In this video, we're going to continue our discussion on Chapter 3. This is Section 2, in which we solve systems of linear equations algebraically. Again, our objective for this video is to solve a linear system of equations using algebra. And the only new vocabulary that we'll introduce is this term called equivalent systems. Generally speaking, when you try to solve a system of equations using a graph or tables of data, the solution to the system may not be clear or even precise. There's an issue with graphing when we're looking for a point of intersection. This coordinate itself may not be perfectly on display and it may not land on a lattice point. Or if we have a table of data, when we have multiple results within a table, we may not actually see two values that end up aligning with one another perfectly. So because of that inconsistency, if you will, we have another method that we can use to solve a system of linear equations. And that is to use algebra. Two specific algebraic methods are the substitution and elimination method. Now, we'll decide when to use each of these two options based on just a couple generic rules. First off, the substitution method is a good idea to use if a variable in one equation can be isolated. In other words, if we can solve one of the equations to get one of the variables all by itself. If we can do that, then the substitution method is preferred. So the process for that is basically three steps with several mathematical components to it. Step one is to isolate one variable in one equation, however many mathematical moves that requires. And then step two would be to substitute the isolated expression for the same variable in the other equation. So once we get, say, x by itself or y by itself, we'll take what that expression is equal to and substitute it in the other equation. And then once we put that into the other equation, the other one will be set up for the other variable. If we substitute it in for x, then we'll be able to solve for y, and so on. Once we obtain that known value, then we can back substitute one more time into the original equation to find the result for the final and original variable. So let's see a couple examples of that. Right here I'm looking at this system. We have two equations that are linear, and I do think the substitution method would be perfect here because I can see that in this equation I can get y by itself pretty easily. So that's the first thing that I'm going to do. Step one is to get this y value by itself. Now it's not really that hard. In order to get this y value by itself, I'll subtract 2x from both sides of the equation. And I'm actually going to erase that because I think at this point that's kind of mental math. So we'll say that y is equal to negative 2x plus 10. Okay, so we know that y, according to this equation, is the result of negative 2x plus 10. Y is equivalent to what negative 2x plus 10 would be. But if I take this expression value, oops, I don't mean that arrow here. If I take this expression value and now replace it in the other equation where y exists, so right here, if I change this y value into this expression, then when I rewrite that expression, or that equation rather, we will have an entire equation written in one variable. So this is step two. We are substituting this isolated expression for the same variable in the other equation. So I'm going to jot down 3x plus 4 times y. What used to be the letter y will now become negative 2x plus 10. And all of that is still equal to 12 according to the original expression. So now the rest of 2 and even part 3 kind of go together here. Our job is to simplify this side of the equation and solve for x. So it looks to me like this 3x we'll leave alone for a moment. This 4, when we distribute it in, I think is going to become a minus 8x. And then we have a plus 40 equals 12. We'll combine like terms to make negative 5x plus 40 equals 12. Let's subtract 40 from both sides. This will further isolate x. And now we have negative 5x equals, what's this come out to be? Negative 28. So x is going to be the result of negative 28 divided by negative 5 after I divide both sides of the equation by negative 5. Now I'm okay with leaving answers as a fraction, although the negative signs would cancel out. So negative 28/5 is fine if you wanted to reduce the fraction. That's what you'd have. Or we can reach for a calculator and get a decimal result. 28 divided by 5 ends up being 5.6. So what we know right now is that the x value that solves this system of equations is equal to 5.6. Now that I know that x is equal to 5.6, I can excuse me, I can back substitute one more time into one of the original equations. And here's nice. We don't really care which equation we go back into. I'm going to place the 5.6 in place of x in this equation because it'll be real easy for me to get y by itself. So if I write 2 times 5.6 plus y equals 10, then whatever 2 times 5.6 is, I'll need a calculator for that. So 5.6 times 2 ends up being 11.2. 11.2 plus y is equal to 10. So now we can subtract 11.2 from both sides, and we've got y by itself, which is negative 1.2. And there you have it. We've now solved this system of equations. We've identified both the x and the y value that would satisfy both of the equations. We can, of course, report our answer like this with 2 boxes, or sometimes we prefer to see our answer written in coordinate or ordered pair form, and we can report our answer this way as well. When you see this question in Math Excel, I believe the blue text after each problem will indicate which method they prefer. So in this example, number 2, again, I think that the substitution method is the way to go because it looks like up here we can get x by itself. So go ahead and pause the video now and try to get x by itself and use that expression to substitute in the second equation. Try this on your own and resume playback in a moment to check your work. At this point I've taken several steps. Step number 1 was to get x by itself because I think that was easy to isolate. So we subtracted 3y from both sides, and we've got that. Then I used this 3y plus 5, negative 3y plus 5, and I substituted it in place of where this x was in the other equation. So we needed negative 2 times something to subtract minus 4y. So here's that negative 2 times something. The something happened to be the expression that we had isolated. And then I took the time to distribute. Negative 2 times negative 3y, negative 2 times 5, and I've combined like terms. And to finish this out, we'll add 10 to both sides, and then divide by 2, and y would be equal to 5 divided by 2, or in other words, 2.5. So here we are again, almost finished with the problem. We've solved for one variable, but we do need to go for the other. So let's back substitute into one of the originals and solve for x. Pause the video now again and solve for x, and resume playback in a moment to check your work. So in this case I chose to use this top equation. Again, I chose that because x was isolated and that's easy to solve for. So if we substitute a y value of 2.5 in place of the letter y, we have x plus 3 times 2.5 equals 5. These two multiply to make 7.5, and I subtracted that to the right-hand side, and it looks like x is equal to negative 2.5. Again, those two answers are good, but if we wanted to report it as a coordinate or ordered pair, or perhaps we were instructed to do so, we'd want to report our answer this way. An x value of negative 2.5, but a y value of positive 2.5. And that looks like a pretty good answer to me. So again, this was the substitution method, and the substitution method is usually my choice when it's easy to get a variable by itself. In both of these cases, one of the equations allowed us to isolate a variable. So again, I thought the substitution method was a good choice. In the next set of problems, I suggest the elimination method. Now we will use the elimination method because the additive property of equality allows us to add two equations with one another. So we can actually combine these two equations with one another. These 1 and 2 equations can actually be combined with addition or subtraction. Sometimes this makes it possible to eliminate, that's where the name comes from, but sometimes that makes it possible to eliminate one variable entirely from the pair of equations when we do so. Now there's a whole further discussion of this in what we would call linear algebra, and there's also another method that we would call row operations that allow this to occur, that describe what are all the legal moves to combine rows together. We're not going to go through that in this video, but if you'd like a further description as to why this method works or why we're allowed to combine these together, then do a quick search online for row operations or row operations with algebra, and I'm sure that you'll find some videos that further describe this process that we're going through right now. But in any event, we're going to combine these two rows together. Now I'm going to pretend like this bracket isn't here for right now. That's kind of getting in my way. But what I am going to note is that if I took this first row, I'm going to call it row 1 across the top here, and added it with row 2, so in other words, if I just added these two rows together, let's pretend that there was just a big addition sign between these two rows, then that would mean that I'd have to combine like terms when doing so. And interestingly, a 4x plus a negative 4x, or in other words 4x minus 4x, that ends up equaling 0x. Or in other words, these two terms disappear. The variable itself, x, disappears. As we move on, we see that 2y plus 3y would become 5y, and 9 plus 16 would become the number 25. Interestingly, if 5 times y is equal to 25, then when we divide both sides by 5, we see that our y value ends up being 5 itself. And this ends up being part of our solution. So y is 5. Let's go after the x value. And just like we did with the substitution method, we have to go back to one of these original equations. And it doesn't matter which one, but we'll go back to one of the originals and back substitute this value of y. I'm going to use this top line. 4x plus 2 times y, well, we know that y is now equal to 5, must be equal to 9. So that tells me that 4x plus 10 must be equal to 9. After I subtract 10 from both sides, we know that 4x is equal to negative 1, and x therefore would be equal to negative 1 divided by 4, or x is equal to negative 0.25. And again, we've solved this system, but this time we ended up using the elimination method. Negative 0.25 for our x value, and 5 for our y value. Here's another. Can you tell which variable is going to cancel out? I bet you can. So again, I'm going to pretend like this brace is not here, this bracket's not there. And I'm going to note that if I add these two rows together again, the y variables this time are going to end up canceling. 8y plus a negative 8y will cancel. Now it's worth noting here that if this was a plus sign in between, technically it's okay to actually subtract the two rows from one another. And if I had 8y take away 8y, that too would have gotten these to cancel. So we might see that as another example elsewhere, but I just thought I'd share that with you now, just as a side note. But this is going to require an addition. 8y plus a negative 8y is what it takes to cancel. And in the act of adding these two rows together, negative 2x plus 5x will be positive 3x, and negative 8 plus 20 will equal positive 12. Now divide both sides by 3, and x must be equal to 4. And now that we know that x is equal to 4, we can back substitute in one of the originals. I'll take this one, the top one again. Negative 2 times 4 plus 8 times y must equal negative 8. This looks like negative 8 plus 8y equals negative 8. So we'll add 8 to both sides, and we end up getting 8y equals 0. Well, that's interesting. By adding 8 on both sides. They end up canceling on both sides, and that's okay. Now 8 times something has to equal 0. Well, if we divide both sides by 8, we'll see that y itself has to be 0. So when x is 4 and y is 0, we have a solution to both equations. Therefore, it's the solution to the system of equations. So let's finish out this video with an application of a systems of linear equations, and I think we'll use one of the two methods from today's video to solve it. We have a music store that offers piano lessons at a discount for customers that are buying new pianos. The cost for lessons and a one-time fee for materials are shown in this advertisement. So if we look closely, you can buy 6 lessons for $300 and 12 lessons for $480, and that includes the one-time fee. Now, unfortunately, we don't know what the cost for each lesson is individually, and we don't know what the cost for the one-time fee is. We're only seeing the total cost for the entire package. So you might think that you're getting a better deal with the 12 lessons. We usually are when you purchase in bulk. But a good math student might be curious and want to find out exactly what the cost per lesson is in either case. Who knows, maybe you're paying the same price in either case. And actually, I believe that's what they're implying here. There is no benefit to purchasing in bulk. Because there is no benefit to that, we can actually answer this question. We know what the cost per lesson and what the one-time fee would be, assuming that there's no greater benefit for buying in bulk. So what makes this difficult is that we don't have an equation to work with. We have to build that ourselves. And I believe once we get the equation built, then the process will be very similar to what we've seen before. So one of the things that I like to do when approaching a word problem is I like to think about what my variables end up being. My variables end up being the unknowns in the problem, or what the question itself is asking. So we need to know the cost of each lesson and the cost for the one-time fee. So if I let those be represented by the variables x and y, I think we can build an equation from there. So again, I'm going to make a note that x is the cost for each lesson, and I'm going to let y represent the cost for the fee. Now that starts to make a little bit of sense to me, because if I look at this flyer, I see that $300 is the total cost if I get 6 lessons, so 6 times the cost of each lesson, plus y, the unknown fee. So whatever 6x plus y is, that's going to end up equaling $300. Moreover, if I bought 12 lessons, the total cost would be $480, and $480 is the result of 12 times the cost of each lesson plus the one-time fee. So I think we've got a pretty good system of equations here that we can work with. I'm going to eliminate this bracket just to make the math a little bit more easy. Do you have a suspicion as to which technique we could probably use here? Well, in all honesty, based on the descriptions I've given in this video, either one would work. In either case, I could isolate y by itself, and we can go with the substitution method. Or, you know, what I think I prefer here is the idea of elimination. If I add these two rows together, if I subtract these two rows from one another, then we're going to be able to get these y values to cancel. Notice we have to use subtraction here because a positive y take away y would leave me with 0. So let's see what we get. Let's take 300 and subtract 480. That's negative 180. And then if I have 6x take away 12x, that leaves me with negative 6x. Now to get x by itself, we'll divide both sides by negative 6. And x by itself is equal to 30. So we'll say something like this. The cost is $30 per lesson, since x was supposed to represent the cost per lesson. Let's take that known x value now and substitute it into one of the originals. Doesn't matter which one. Let's go with the top. 300 is the result of 6 times $30 per lesson plus y. This would mean that 300 is equal to $180 in total for the lesson costs plus our unknown original fee. Let's subtract 180 from both sides, and that'll leave us with $120 representing our y value. So the cost per lesson is $30, and the cost for the fee is $120. So I hope these examples help you better understand this notion of systems of equations, and I also hope that you realize that the algebraic method sometimes is really nice and perhaps even quicker than using a graphing or a table method that we saw in the last videos. It will require a little bit more algebraic work, of course, but that's the trade-off. There's a benefit to using the algebra as opposed to what I would say is brute force by graphing and setting up a table. If you have further questions, please let me know. Otherwise, thanks for watching.